Alrighty, in this video, I'll take a look at the idea of the force of gravity that acts between objects. And we find that using Newton's formula for universal gravitation. We only solve for one force of gravity, because whatever my objects are, it could be the sun and the earth, sun and earth. The force with which the sun pulls on the earth is exactly the same size as the force that the earth pulls on the sun with. Now, that force, therefore, we solve for both, but we need information about both to get its value. And ultimately, if I wanted to go back and see what happened to the motion of the objects, I would have to take this back to some version of Newton's second law of motion to actually look at accelerations and things along those lines. In this particular example, I have two moderately sized objects, 25 and 73 kilograms. They're not going to have really big sizes. They're fairly small. Now, the reason I bring that up is that when I do have problems involving something like the sun and the earth, the volumes or the sizes of the objects does become important. When I'm looking at measuring this distance of radius, it is from the center of one object to the center of the other. Well, for small objects, simply the distance from the surface of one to the surface of the other is sufficient for problem solving. But for something like planets and moons, where the distance to the center adds on another so many thousands or millions of meters, I have to take that into account. So if I was looking at something such as the sun or a planet to its moon, I would need this radius plus this distance from edge to edge plus that radius. And all of these three summed are what go up here, not forgetting to square them in the equation. So, needless to say, you'd have to be given that information, but if someone goes to the trouble to give you all that information, make sure you do use it properly. So this particular example, my objects are probably not very big, so we're only given one distance, and that is 14 meters. To solve for my force of gravity, I just simply plug into the equation. Force of gravity equals, and the first thing I run into is that big G. Remember, he is a constant. His value does not change no matter where you are. 6.673 times 10 to the minus 11. It's Newton times kilogram squared over meter squared. Meter squared over kilogram squared, but I'm not going to write that out for you right now. Do not forget, however, to use him in your problems. Don't leave him out, and don't confuse him with little g. The mass of one object, 25 kilograms, times the mass of the other, 73. My distance, 14 meters, and square him. And when I solve, my force of gravity turns out to be, let's see, what did I find? 6.2 times 10 to the minus 10 newtons. Just because it's gravity doesn't mean he's not measured in newtons. But now what if I'm asked to solve for a different variable in my equation? Something like distance. Let's say I'm given a mass of one object of 1,500 kilograms, a second, I'll call him M1 and him M2, of 3,200, and I'm told that the force of gravity between them is 4.5 times 10 to the minus 8 newtons. I want to know how far apart are they. Well, I still use the same formula. Force of gravity between two objects, Newton's constant for universal gravitation, the mass of each object, distance between them squared. I put my information into my formula. 4.5 times 10 to the minus 8 Newton equals my value for big G, which I'm not going to write out right now for you. I just did. 1,500 and 3,200. Looks like I'm running out of room everywhere. So I'm going to go vertically, just because I'm a rebel. Zoop. Divided by r squared. To solve this problem, I would cross multiply. So I have G times 1,500 times 3,200 is 4.5 times 10 to the minus 8th newtons times r squared. Divide both sides by r squared, divide both sides by 4.5 times 10 to the 8th, which would cancel him over on this side. And then don't stop. At this point, I'm solving for r squared. Whatever answer I get, don't forget to take the square root. So on your calculator, don't forget to do that little guy at the very end. And in this particular problem, it works out to be 84 meters. So you could be asked to solve for a mass, or another mass, a distance, or the force of gravity. The one guy you never have to solve for is him. He's always a constant, again, no matter where we are in the universe. Now, if I go back, though, to that original problem, where I found a force of gravity of 6.2 times 10 to the minus 10 newtons, there is a chance that a problem could ask you to go farther. This problem might actually be a problem about centripetal force. Remember, centripetal force is a job description, and gravity does serve that job quite nicely. So I might have to go through the effort of finding the force of gravity first, bringing him over to this formula, and then potentially solving how fast is the moon going around the planet, or at what distance he was orbiting, or something along those lines. But I might have to take things one more step. Another common one more step with centripetal force is with friction. You might have something like a bike that's going around a track. Well, friction is actually the centripetal force that's acting to keep the bike in a circle. You might be asked something about the bike is going around the circle. We know the size of the track, the radius is so much. And we're asked, what's the speed of the bike, or the motorcycle, or the car? Well, in this case, there's your centripetal force. He's friction. Look for information in the problem such as, oh, they gave you a coefficient of friction. I've got the mass of the object, which means I also have the object's weight. Why would that be important? Well, remember this formula? Coefficient of friction is force of friction over normal force. Well, if we're on a flat track, that weight right here, there's your normal force. So if the problem gave you this guy, oh, I've got force of friction. And then force of friction would come over here to this formula, just as gravity could in the last example, and solve for speed. So when we're dealing with the idea of gravity or friction, normal force, any of the forces, sometimes you have to solve for them first, bring it over to a centripetal force equation, or we could turn a problem like this around. Could have asked you to solve first for centripetal force using this information, bringing him over to this formula with then the weight of my bike or my plane or my car, who knows what it is, solve for coefficient of friction. So it could go the other way as well. So this little video, I know I kind of veered off a little bit about gravity and went into some other areas, but specifically centripetal force. But this particular formula allows me to calculate for a force. If he does a job, I might need that force to do to find out what type of job he does and something about that particular job. So this formula, you're given this on your formula sheet. Don't memorize him, but don't forget to use him, and don't confuse him with little g. Remember that that is in newtons. Mass and mass must be in kilogram. Distance must be in meter. So watch out for unit conversions, another place that we can trip up on this particular formula. Alrighty then. Any questions about Newton's law of universal gravitation? Bring them to me and we'll see what we can do with them.